We have speaking us today Matt Walter. Matt works on robots in the land, in the air, and under the sea. On the surface of the sea also? Just under the sea? Just under the sea, no surface of the sea. And we'll be talking to us about today about how to teach these robots using demonstrations and rewards.
Thanks, Nadi. And so this work, I'm going to present a bunch of work which was really done by other people, not me. So a bunch of the collaborators here, some from TTI or were at TTI and have since left. University of Chicago, and one plug, Shuifeng Liu here, is defending his thesis on Tuesday, was it December 2nd in Qurar. So if you find any of this work interesting, or there are things that you don't understand, which I'm sure there will be because you presented better than me, go to his defense. And so what I'm going to talk about is, as the title suggested, which was generated by GPT, a bunch of projects that we've been working on the last couple of years on robot learning, so reinforcement learning and imitation learning. And the goal with a lot of this is to bring robots outside of labs and outside of traditional factory, highly structured factory settings, onto our streets and into our homes and into our workplaces. And there's a lot of attention, as you may have seen in industry, to try to get robots really to do useful things in our home. Just yesterday I found out about another company that's trying to sell a robot, or they plan to sell a robot that can go in your home and provide some utility. This video came out, or this, I should say, the video came out by 1X. They announced a product that you can buy for $20,000, which maybe actually is reasonable. And the idea is this robot's going to come to your home, and it can do laundry. Somewhere in the video it shows it watering plants outside, unloading the dishwasher, acting as a companion for people. Of course, if you watch the video, you see the people that have this, they drive Porsches and they live in very nice houses because still $20,000 is not cheap. The secret, though, is that during the first year, at least, most of this is not going to be autonomous. There are going to be people sitting somewhere with a bunch of monitors watching camera feeds from this robot, effectively teleoperating it. This video came out probably last year from from Physical Intelligence with the Aloha-like platform, folding laundry. So there are people doing a lot of work really trying to get robots to operate in our semi-structured or unstructured environments.
Where'd you get one?
Huh?
Where'd you get one?
The one on the right? 1X. I think you can buy it now. I think it's $500 a month or $20,000. Yeah, see, there's the Porsche.
Very cheap.
I don't have a Porsche. So
No, the one on the left. Yeah, the one
on the left you can't buy it.
Oh, okay.
That would be more
actually
affordable.
works.
I don't know if either of them work, honestly.
And what is the toilet? They will go for you. Is the toilet? What is it?
I don't know what they'll do there.
Good.
It's not clear how generalizable these methods are. But all of these, this work and the work that we do and a lot of other people do are going to formulate this in the context of what's known as a Markov decision process, which is a fairly simple framework where we have some agent. This agent might be the policy. We might typically refer to this as the robot or the agent that's the software that's controlling the robot's motion, and that's interacting with the environment. And it's a pretty simple procedure where the agent executes some action, might be joint torque in the case of a manipulator, steering gas brake in the case of a car, in the environment, and then the environment returns or tells this agent what the next state is, and that process is stochastic, and then it gives it some reward. This is a very standard setting, and so underlying this is what's known as the reward hypothesis, is that all goals or tasks that I want an agent to do can be formulated in the context of maximizing a reward. And maximizing it in expectation because of stochasticity, right? So uncertainty.
Yeah. So it's in what sense is it a hypothesis? It seems like it's an assumption in some sense.
It's an assumption. Yeah. We're assuming that
It's not like this is true or not true. It's just we're going
to assume
be
that
interested in goals for which this is
which
true.
there is it can be formulated as maximizing expected return or sum of reward. Right? And so
What is the difference between RT and ST?
ST is the state. It's the image. It's the pose of the robot. RT is the points. You can think of this sort of like a game. It's the points that you get. You do well in class when at least when I was a kid, you did well in class. We got to go to Pizza Hut or something. So we get some prize. The RT is the prize that you get. Yeah.
So the environment contains things besides the observable state. So So let's say you're a robot moving around, you move, so you are now in a different position.
Yeah, so in this framework, we're assuming that the state is observable.
I see.
Now, there's what's known as a POMD piece, a partially observable markup decision process, where the state is not, we get a noisy observation of the state.
But the reward then is still observed.
This reward is observable. Now, it's, we might not get any reward until the end, and we'll talk about that, that's sparse reward. But the state is observable. And one way you can think, maybe one way you can sort of bridge POMDPs and MDPs or RL is think of the state as an image. That's what people often do. And in that case, the image is observable, but there are lots of parts of the world that you don't observe, that are not captured by the image, by an image. Right? Okay, so we can model this a little bit more formally, and it doesn't really make, it's not too important, but we're going to represent this as this tuple. So we have the state space, that's a set of states that the environment can take on. Action space, a space of actions available to the robot. We have this transition function, which is, in the case of RL, is not known, but it's this distribution over future states given the current state and the action, and it's a markup process. We'll model this as a first order markup process. Sorry, it's a markup decision process. We'll model this as a first order markup process. We have a reward which is nominally a function of the current state, the action the agent takes, and the subsequent state in the general form. And we'll have some discount factor. This discount factor is just basically discounting future reward. So our goal, again with this reward hypothesis, is that whatever I want to do can be formulated as maximizing the total return over some horizon. So maybe it's an infinite horizon. So in the future, I want to maximize how many points I get in the game, how much reward I get. Again, with discounting. So I'm going to reward immediate reward. I'm going to weight immediate rewards higher than future rewards. And so that's RL, or that's MVPs. With deep RL, all we're doing now is we're going to model the agent, the policy, using neural networks, but the rest of the framework. And as the footnote says, if we knew the transition function and we knew the reward function, we could solve this we could solve this to be a dynamic program. RL is challenging for a number of reasons because we don't know the transition function, we don't know the reward. The only way we get reward is through trial and error. Basically, that's what the agent is going to do. It's going to learn through trial and error. So let's think about this arguably simple ant-like robot, really this quadruped here. So it has 4 legs, 2 joints in each leg, and we can control, let's say, the joint torque. Right? So there's a joint here at the body, and then a joint here. We can control the torque. And the goal with this robot is to navigate this maze. So the robot or the agent starts in the lower left, this arguably pretty simple maze. We want to get to the upper right. We get near that green circle, we get a point, 100 points, whatever. But now the question is, so with small action space, what is an appropriate reward, right? Because that's the only way that the agent gets feedback. That's the only signal that the agent gets to indicate that it's done something good or done something bad, maybe with negative rewards. So the easiest thing for the agent in terms of learning is to provide a dense reward, meaning that at every time step we'll provide the agent some indication of how well it's doing or how well it did in that time step. But for many tasks, that's difficult to specify. If I want a robot to load a dishwasher, say, so my goal here at the end, the green circle corresponds to the dishwasher being loaded. It's not clear to me, maybe it is to you, what would be a dense version. I mean, I can come up with some heuristics, but it's not clear how I could come up with the right dense reward. Or say a robot, and I'll show a video a bit, a robot walking or running. I know running when I see it, and I know good behavior, you're running, that's quote unquote natural, but it's difficult for me to define this as a dense reward. So that's hard, but makes the learning problem easier. Much easier for me is just give it a sparse reward. Okay, I'll give you 100 points. I'll give the ant robot 100 points when it gets to the goal. But otherwise, I'm not going to give it any feedback. And you can imagine that's a challenging problem. Why? Because in the beginning, the policy is randomly initialized. It doesn't know anything. So it's going to do basically motor babble. It's going to move the legs around. It's going to do, you can imagine, and this robot is pretty easy to stay stable, so it's probably not going to fall down. But it's going to move around in here. What you need is you need the right sequence of motor babble to get it to the goal. And that's the only time it's going to get points. So if you imagine 2 trajectories of the robot taking, one where it basically just stays here, and another one where it gets close to the goal but doesn't get there. With sparse reward, in this extreme case, they both get 0 points. So to the agent, they both look equally good or equally bad. But clearly one is better than the other. One almost got close to the goal, the other one didn't leave their room. And so, but this is what we see. So what I'm going to show here is a heat map that David generated using a standard RL method, soft actor critic, SAC. And what we're showing is this heat map over I don't know how many episodes, but where the agent visited. So the agent was able, through this effectively motor babble, to get outside the room, but it didn't get anywhere near the goal. So it has no idea that the motion that got it out here is useful. So there's no signal that it has to learn, right? And so because of this, RL tends to be very sample efficient. Sample inefficient, right? We need a lot of trial and error before we effectively stumble on the goal. And once we stumble onto the goal, now the question is, well, now I need to basically propagate that reward back to figure out, well, some of the things that the robot did to get there were good. Some of them were not so good, didn't help, right? And so how might we deal with this? This challenge is known as exploration, right? We need to explore. And so we'll talk about one way that we've done this, and this is David's work, subwords as skills. But I'll show how some people deal with this. So one is, we say, let's forget sparse reward, let's just densify the reward. And so I'm showing this video, I think this is from, it's a humanoid, I don't know if it's DeepMind, I don't know what control suite, but it's a humanoid robot, you may have seen videos. And so what we can do is, well, we can try to come up, the goal here is to get this robot to run, this agent to run. And so I can try to think of some dense reward signal that might incentivize this desired behavior. And that's not trivial. So I'll show you what policy was learned. I mean, the robot it's running, right? It's not falling, and this is a robot, this is an agent that is easy to fall. So it's doing something useful. But I don't know about you, but I don't run like this, right? It's not at all natural. And this is oftentimes what you see. The agent is it's trying to exploit, trying to optimize this reward that it was given. This is dense feed signal. And I just show a screenshot. Now,
why is the fact that it's not natural
maybe
relevant here?
It may not be. It may not be.
I mean, hardware reasons. You put this on the hardware, all of a sudden there's going to be collisions.
That's true, yes.
You'll have bad usage. Like they're.
Why? I mean,
very
what does that
energy
to do with
inefficient.
natural?
True. Yeah. So maybe.
You could design hardware, sure, that works this way, but I guess if the policy is random for every random initialization and it ends up this way, and your hardware is not perfectly designed for that, then you have a lot of wear that becomes a problem.
Presumably, this does mirror the hardware, the simulation. Hopefully, no, I mean, still, I don't have what natural has to do with it, right? I can't bend my arm over there, but it's very easy to design the.
Every time
Contact
the
with
hardware
reality
the
is the
same
answer.
question.
Yeah.
If you did motion capture on Usain Bolt
Yes.
and looked at how much energy this thing is taking.
Oh, it's a lot more. I'm sure.
So that answer is not
Yeah.
his question.
So it's very energy inefficient. So that.
Okay, that's a different.
that's-
That's
yeah.
a different.
But yeah, I mean, I
natural,
think that
right?
if you want to, if I want a humanoid in someone's home, I think people would pause if the humanoid in the home was moving like this versus something that's more socially acceptable.
No, but that's different. So now you're saying you have a different type of objective here, which is in addition to walking, you also
Yeah.
want it to be pleasing.
Sure. Yes. Yeah. But my point is that that's difficult to. So yeah. So my goal is not just walk; it's to walk in a natural way.
So you're talking about reverse, but like reinforcement logic, if you make mistake, you should be punished or somehow.
Yeah. So this gets punished. If it falls down, it loses 100 points or whatever it is. So it gets punished.
Is it natural to consider the same thing with history, but the robot remembers all previous moves?
Yeah. So typically, that becomes more challenging in the MVP setting.
Some segment of it.
Yeah, that becomes a little more challenging with this the way we're formulating this as a first order Markov process. But you could do something reasoning over trajectories, and so there are other ways to do this. Not via RL, they'll do this as formulate this as trajectory optimization, and they will do things like this. The other thing they can do is, like David suggested, is we put motion capture on someone like Usain Bolt or a person, and we'll talk a little bit about something related to that, where we'll try to mimic the way that people locomote.
So maybe, and that relates to what you mentioned here.
I'll
about
show the
domain
rewards just real
expertise.
quick.
But
Yeah.
maybe instead of capturing symbolic, you can also just define rewards in terms which make physical sense. For example, energy consumption,
Yeah.
stability, maximize velocity.
No, that's what's going on.
That's what we do.
That's what's
Yeah.
going on.
Well,
It seems like
but
in
not,
addition-
you do not include presumably the energy consumption.
We have, yeah. So this is one of the again. This is from a.
Oh, I see.
This is I think the 7th version of the reward that they tried. This is from a
So
tutorial.
this is just a failure to.
Optimize.
It might be that I'm picking, the way that I'm expressing this is not, my functions are not right, or here there are not, I guess there should be weightings in here,
I see.
But
but I
again, it
didn't
seems
pick the
like,
right weightings.
but it seems like it's it. There's another objective you're not included in here, which is you want it to be visually pleasing to a human.
Yes, and I don't know how to, I don't have,
Right,
that's,
and that's
yeah,
completely
yes,
separate
that's
from being
separate,
energy efficient, right?
that's separate, yeah. And I don't know how to
You're not
formulate that
including that.
unless I'm trying to mimic the person. Okay, so so this is one approach, right? We get a domain expert to try to densify the reward, to come up with maybe some, heuristic that captures what's quote unquote natural. The other approach is let's instead introduce some temporal abstraction. So now what that means is my policy is not reasoning over immediate actions to take, which might be running at 10 hertz, 100 hertz. It's reasoning over some longer horizon action. Sometimes people refer to this as options, if you're familiar with an options framework, or skills or behaviors. Macro actions go by various different names, and they're different, but they're related. But so we're gonna refer to these as skills, and these are subroutines. So something that's more temporally extended, that makes the exploration easy. So now to navigate the maze, it's not I have to get the right sequence of 1,000 motor babbles that get me to the goal. Now it's the right sequence of maybe, 20 actions, because now my actions have a longer horizon. Now the question is, well, what are these skills? How do we identify them? Right? I'm not, I probably don't want to just chain random actions. That's not going to help me. I want them to be, quote unquote diverse. So if you're here, anyway. So there are various ways of learning these. So I can learn these from rewards. I can try to learn these from demonstrations. But existing methods for learning these, discovering these skills, are computationally expensive. And so what we were asking, or really what David was asking, is there a better solution? And so we looked at some of this with Falcon, as a former student here. And so the inspiration for this is tokenization methods for language models, which uses byte pair encoding, which again is a method that predates language models. It was used for file compression. And the idea is, well, let's treat actions as characters. So now what that means is now our action space is discrete. So we have a discrete set of actions, and each action is a character. What I'm going to do is I'm going to take a sentence, I'm going to take text, and I'm going to look for I'm going to take trajectories, which are sequences of actions. You can think of that as sequences of text. And what I'm going to do is I'm going to look for repeated patterns in these demonstrations or in this text. And I'm going to refer to those repeated patterns as skills, as these macro actions. And so that lets us do in the case of language models is, we can model longer context with less memory. In terms of file compression, we can represent text with fewer bits. And the algorithm itself is rather simple. So we start with some strings, so some sequence of characters. Again, in our case, these are actions, but here, you can think of this as really just characters with some vocabulary. So this is A, B, C, D. And what I do is I look for frequent pairs. So in this case, AB appears several times. So I'm going to refer to that as a symbol. I'm going to call that X. And so now this sequence AA, BC, AB, DC becomes AX, CX, DX. Then I'm going to go through that again and look and see, well, now are there other repeated strings that I can compact into a symbol, or in our case, a skill.
This is in demonstration data that you're doing on? Or
We're doing this in demonstration
rollout
data.
trajectories and demonstration
We're doing this in demonstration. So yes, we have to have access to demonstrations. Yep. Okay, so this is the basic idea. Very, very simple. And so that's what we do. So yes, so we have access to a set of demonstrations. Each demonstration is a trajectory. So this is at the navigating the maze. This is maybe a video of, or someone controlling a robot to walk. So we get the sequence of state action pairs. Again, we get a set of them, n of them. And again, we're assuming we have characters, so we may need to discretize, if the action space is continuous, we need to discretize these to get characters. And then what we do is we just apply tokenization. We apply byte pair encoding specifically to get these skills. So very simple in spirit. And so just a visualization of this. So we have some, see it in my end, but not here. Here we go. So we get so what I'm showing here are two demonstrations. We actually obviously have a lot more. And when we look at these demonstrations, we look for repeated patterns. So over here, we can see that, this is red and orange, so they're different here, might be able to not be able to tell because the colors are similar. But here, they both have this repeated pattern, turning to the right and then turning to the left. Which again, you can imagine for ant maze is useful for navigating around. And again, I should say for ant maze, these actions are not center of the body. It was an 8-dimensional action space, so 2 joints per leg. And so what we're going to do is we're going to merge them. So we're going to call that this new symbol X, this new skill. Then we're going to repeat this process. And what we get is, if we look at this demonstration again, this is a sequence of actions for each one of the joints. And in this case, causes the robot to move forward and turn a little bit to the right. And now these are the actions that and we can have a bunch of these. And these are the actions that our policy is going to reason over. And so now you can imagine that it's not motor babble anymore. When my policy is randomly initialized, it's picking among, it might be picking randomly among these actions, but these actions are now meaningful. So you can imagine now that it could be possible to chain these, it might be 10 instead of 100 or 1,000, that let us get to the goal. Right? And so we'll look at some of the skills that we learned for ant maze. So in the lower left, we see this ability to make tight turns, so it's turning in place. Again, you can imagine that might be useful. We get this from demonstrations. We get some, wider turns here. And then we get just forward motion from these demonstrations. So really simple, which is good, and I'll talk about what the benefits of that are. So we evaluate this in a series of domains. Again, these are fairly standard in the literature for people who are looking at skill abstraction or sparse reward RL. One of these is, again, ant maze, right? This quadruped. Sparse reward, it gets to the goal, it gets a point, otherwise it doesn't get anything. Kitchen is another task where we have this Franca-like manipulator, and it's trained to do a series of subtasks. So a subtask might be open the microwave, turn on the burner, move the kettle, flip a switch, open a cabinet. And it gets a reward of 1 for doing each subtask. And then we have this platforming game, coin run. And so again, we need demonstrations to learn to do this tokenization, to learn these skills. So for ant maze, we look at scripted suboptimal demonstrations. The demonstrations don't need to be perfect. Now, of course, if all the demonstrations just spun in place, it wouldn't be very useful. But for ant maze, we get suboptimal demonstrations. Kitchen comes with these VR-based control of this robot. And then coin run, we look at easier levels, and we get data of humans playing these easier levels. And so we compare this with standard baselines. One is just soft actor critic, sort of the standard RL method, using either a continuous, because again, ant maze is continuous, we have to discretize. Coin run is discrete. Kitchen is continuous, so we have 2 versions of SAC, soft actor critic, one with the standard with continuous actions, one with discrete with k-means, and then different skill discovery methods. So one that uses a VAE, and then this autoregressive method, state-free priors. And I'm showing the performance here, and you can see, well, again, it's a sparse reward problem. For ant maze, again, these are different sizes of maze. So U maze is a simple maze, medium is larger, and large is larger. Kitchen maze, you can see that, well, soft actor critic just completely fails. And I'll show a visualization of why that is. SAC discrete, so discretizing the action space still doesn't help. It fails. The baselines are a little bit better. In some of these, ant maze is really challenging. SFP is able to do ant maze large. Whereas our method now is able to get reward for each task. Now the variance is high because these are sparse reward settings. But with this simple way of using tokenization to learn these skills, we can solve these tasks that previous state-of-the-art methods could not. And again, just showing some visualizations, but we already saw the numbers. So plots here, higher is better, that's the return. This is steps. So we see some of these, like here, this is SSP, this is the VAE-based method. It is able to do well for U-maze, but you can see that our very simple subwords as skills method does far better. Again, there is a high variance, especially in the large, because it is because of the sparse reward.
So what is this variance over? I'm a bit confused about this.
Different random seeds.
What
The environment.
during
The policy training.
Yeah, everything.
during
And the initialization, and like slight random
Well, but if
initialization
it's
of the.
during, I mean, it's easy to verify here, right? So, I mean, why do you get such high variance over the training? I mean, you could just train 3 times and take the best one, you'll cut your variance.
It's 0, 1. Yeah, I don't like you train 5 different random seeds and
You might not discover, you might
you
not get to
random
the
samples over each one. So some of these are actually failing to learn entirely. Some of the
Yeah,
random
some of
seeds
them
are
fail,
training.
exactly.
Training.
So why not just train 10 times and take the best one?
You can do
You
that.
could do that, yeah.
Wouldn't that like completely cut your, if that's
Yeah.
the source of your variance, wouldn't that completely cut your variance?
Yeah, yes, yeah, but we're showing that, to be, I
But
think,
like you
for-
care, why is this important? Is that like if the task is if no seeds make it, like maybe you
Yeah.
can't detect anything, right?
No, I
But-
know, this is
But
why.
like it could be that like you say, okay, my training isn't working. Is it working on some new task? Is it not working because we picked a bad random seed, or is it not working because of the method?
Yeah.
This is what I'm trying to understand here, right? If it's not working because of a random seed, I mean, that's like something internal to you, you should fix that, right? I mean, it's not.
Yeah.
But that's,
So I'm
but
trying
that,
to understand
and that's
if
what a lot
variance
of people,
represent a real
that's what a
thing
lot of
or-
people do in RL, but I think that they hide that, and I think
Why
that,
is, why is that? Okay.
just to hold that it's a really challenging it's a
Because I
challenging.
guess it's a question of like, if there's only one seed out of 10,000 that you
Yeah.
try that
No,
works,
but
then that
that-
says something about whether
Yes,
the
But
algorithm is
then
actually
you-
useful. in
But your
practice.
expectation is half here, like half the seeds would be good, just try 10 of them and you'll succeed in like almost 100%.
I agree, but like we wouldn't know that unless we tried 5 seeds.
So, I'm confused because
And again, this is coin run and kitchen, but we can skip over this, but why is this hard? And again, I showed this visualization before, it's probably the same one that I showed before, so this is SAC discrete. Again, this is where after some number of episodes, I don't remember that here, David probably knows, but the state visitation, right? So it's getting nowhere near the goal. SFP, same. SSP is a little bit better, but still, it's not visiting near the goal, so it's not getting any return. So it has no indication that it might be doing something useful. This is the visitation with subwords as skills. So it's doing a nice job of covering this maze. And so again, for the seeds that do get 0 reward, the state visitation heat map looks very similar to this, right? So it's for many of them, it's getting very close to the goal. So it's still doing a nice job exploring, but it's not quite getting there. And that's why it's not getting any return. Okay, so another benefit of this, so just the fact that again in our experiments it tends to work well. It's also ridiculously fast compared to the baseline. So there are 2 things here, right? There's one is how much time does it take to learn the skills, and then depending on how I model the skills, what's the compute for say the forward pass through the neural network? Right? So we look at SSFP, and so just for context, I don't know what that's. These are in seconds. This is about 36 hours for SSP to learn a set of skills. SFP is better, 18 times better. It's 2 hours. For subwords as skills, it's 3 seconds to learn the skills, right? Because it's just this tokenization. The rollout again, we don't have a neural network that we have to pass through, so it's 0.007 seconds to call up a skill essentially. The others are not terrible; they're orders of magnitude slower, but at least they're second or sub-second. Now I guess I'll probably skip over this, but another thing we've looked at is, can we use these skills for transfer? Can we learn skills in one domain, say in this case learning it from AntMaze medium, and how portable are they? So we learn skills in AntMaze medium and say now we take those skills and we try to get a policy to do a different maze, which is UMaze, so structurally different. And it works quite well, even with just you looking at 1% of the demonstrations. So that's one way that we can deal with this exploration problem. Another, again, analogous to what David was mentioning, is let's try, and again, some of you have seen this before, let's try to watch Usain Bolt run and try to mimic his behavior. We're not going to be running, we're going to be, in this example, driving, in Mario Kart here. What we're going to do is we're going to collect a bunch of demonstrations of people driving, and for the most part, we're going to assume, or what most existing methods assume, is that these demonstrations are optimal, right? So we have experts that are giving us data. And so what does this data look like? This data looks like trajectories. What is, again, if you remember, what is a trajectory? It's a series of states and actions. So an image, maybe, and what was the steering, gas, and brake at that point in time that the user executed. And they draw, and they're driving, so we keep collecting these sequences, and that gives us one trajectory. And we get a bunch of them. And then what we can do is we're going to take these, this now becomes a supervised learning problem. We're going to train our policy, now it's going to be a neural network. And we're going to train the policy to match he's at this expert behavior. So if I have the same image, or if the policy has the same image, it should predict exactly what the demonstrator did. And this is not at all new. People have been doing this for a long time, and I know several of you have seen this video before. So that Alvin here, so this is an '88 paper using a neural network to train an imitation learn policy. It's a nice History Channel video that talks about the history of this. Initially moving, I think it was like a meter per second, and now they're doing actually highway driving, training a neural network via imitation learning. And you can imagine that companies like, I don't know, maybe Tesla is doing something similar with their millions of cars on the road. They have people collecting data. Again, I don't know exactly what they're doing. And these companies I showed that video of physical intelligence folding the laundry. That's what they do. There are a lot of companies now that says, well, basically, let's try to do for robotics what effectively the internet let us do with language models. It's like, if we just get enough data, we should be able to we can just train a foundation model, a robot policy to do these tasks. And so they say, well, let's, if you have enough money, we can pay people to just collect as much data as possible, teleoperating these robots around to collect this data, and we'll train it via imitation learning. Now, but the problem is that a lot of these methods rely on these demonstrations as being optimal. But if you've ever teleoperated a robot, it's not easy. It takes a lot of training to become proficient. And so, at least initially, the demonstrations that you're going to provide are going to be far from optimal. And one approach is let's just throw them out and wait till we get good demonstrations, and maybe that's reasonable. But I think our point is that there's still a lot of useful data that we have in these suboptimal demonstrations, right? And so I showed this video before, Mr. Bean driving. Again, maybe he's driving our Tesla, right? Now, people don't do this, but there are stories of people sitting, shaving, obviously on their phone when they're driving. So what, can we do something in real world settings where we have access to demonstrations that are suboptimal? And so we'll use this term oracle. I know typically I think of oracle as being, sort of the gold standard, but that's what's used in the literature. So oracle is a policy that gives us demonstrations, a person that may be suboptimal. And so the question is, can we learn from these suboptimal oracles? And so let's go with this cartoon example, right? So we have 3 drivers, and we have different environments that we like them to drive in. Countryside, highway, and city. So I have Mr. Bean here. Mr. Bean in the countryside, or I guess is more rural, is not maybe a very good driver. Here's that highway video. I guess I probably should have flipped these. But here he's a little bit better of a driver. He's driving with his mouth, but at least he's paying attention to the road, right? We might have Homer Simpson. Homer Simpson, in the city is not very good. He decides to eat and snack, not pay attention, whatever. He gets angry here, crashes. But anyway, so the idea is we have access to these oracles that are, or these people, these policies, these set of demonstrations that are good in some states and not good in others. And hopefully they're complementary. But we don't know how they're complementary. Now this last one for Seinfeld is where it hits the squirrel, but it's a good episode. But anyway, so the idea is that if I have access to these black box oracles, so I don't know that Mr. Bean is good in the city. I just know I have access, I can query Mr. Bean, or I have access to his data. I don't know where he's good and where he's bad, so he's this black box. Could I figure out where each one is good and take advantage of that to learn a policy? Right? And so we can do this with standard imitation learning now. One formulation of this is behavioral cloning, right, which is basically turning this into a supervised learning problem. And typically the way that that's done is to minimize some KL divergence. So we have some distribution. What I'm showing in black is the distribution over the demonstrations. So this might be, a combination of Mr. Bean and Homer Simpson. The best of, maybe let's assume that they're both good. And so, but the key here is that this distribution is multimodal, bimodal. And depending on how I represent my policy class, if we're minimizing KL divergence, we get this what's known as the M projection if you're taking the graphical models class, which is sort of regresses to the mean, essentially, right? So it's going to try to fit both, and it's going to basically not be good at either, right, essentially. So this line of work, which is again with Takuma and Shui Feng and Yu Chen and some others, Rick Stevens, is to see if can we do better. And just the way that we're going to look at this for context, some things that I think we'll be looking at is two functions. One is known as V is the state value function, and all that this is doing is what we want to do is we want to look at the expected, what's known as the expected return, or the cumulative reward and expectation, right, over the horizon. And so that's what this function captures. We start off, again, we're in some state S. My policy that I'm learning says to take some action. I'm going to take some action. That environment is going to return some subsequent state, S prime. Again, it's stochastic. And then from that S prime, I'm going to get some immediate reward. Maybe, again, in a sparse reward setting I wouldn't, but in a dense reward I'm going to get some immediate reward. And then that's going to bring me to a new state S prime. And from that S prime, there's some expected return that I'm going to get from there onwards to the end of the episode, right, till the game is over. That's what V pi is capturing. So what V pi is telling us is that if I follow policy pi, so the robot does whatever policy pi tells it, how much return do I expect to get? Or what's my expected cumulative reward? That's a state value function. The action value function is very similar, but it's different in that for this time only, I'm going to let myself ignore the policy and let myself follow some other action. So I'm going to parameterize in the action that I take now. So right now, I'm going to let myself take a different action A. This is a function of Q. Again, I have my probability function. So this is the distribution over the next state I'm going to be at S prime. I'm going to get some reward that now is a function of A, not pi. But then what I'm going to do is I'm going to say from then on, I'm just going to do whatever the policy tells me. So what this is useful because this lets me think, well, could I, in this state, S, could I do better than the policy by doing something different now, but then following the policy later? You can imagine if I can, then I can use that to improve the policy. Right? I'll do something differently now, but then follow the policy. But if I do that, that's a different policy. Right? It's a different function because I did something different in state S, even though I did what the policy told me in the future. So now, potentially, I can use this to improve the policy. And so for this, there is this baseline function. And what this is doing is this is basically the function against which the policy can be improved. Right? So V is telling me how good this policy is, and I'm going to use that to try to improve on it. Right? Okay, so what might I do if I have access to this set of our three drivers or our set of oracles? Right? And again, none of them are optimal. Okay, well the simplest thing may be what? I can just try to figure out who's the best driver. I'll pick the best driver. I don't know if this is, maybe it's Homer Simpson or something, right? So I'm just going to follow Homer Simpson's policy. I'll try to mimic Homer Simpson's policy. So now I'll just ignore the rest, and I'll just do behavioral cloning, standard imitation learning on Homer Simpson's policy, right? So that's going to be okay. That's all this is saying. I'm looking at again, this is telling me how good each oracle is, and I don't know it. That's the challenge. I don't know this. So the value function is how good is this policy in this initial state distribution D naught. I don't know it when we'll talk about how we estimate it. I don't know it, but if I did, I could just maximize. And what I'm going to do is I'm going to pick whatever, from this initial state, whatever the best driver is. And so when I'm in the countryside, I'll do what Homer Simpson does, and that's great. But then, okay, when I'm in the highway or city, I'm also going to do what Homer Simpson does, and that's maybe not so good. But that is a viable solution. The next thing I can do is, I can maybe be a little bit smarter, right? What you can imagine what I would want to do is, okay, well, when I'm in the countryside, I want to copy Homer Simpson. But then once I get out of the countryside to, say, the highway, I'm going to copy George Costanza. And then when I'm in the city, I'm going to follow Mr. Bean. That is obviously better, right? So that is this max following policy. And so what it is just this greedy policy that follows the best oracle in each state. So mimics whoever in this state, whoever is the best driver of the three, which still might not be optimal, but the best of the three, I'm just going to mimic them. Okay, so it's clearly better, right? But could we do even better than this, right? So again, I'm going to let this animation play, but I already described it, right? So in the city, it's Homer Simpson, or highway Homer Simpson, oracle, it's Mr. Bean, right? So let's think of a simple example. So we're not driving anymore, we're navigating this one-dimensional maze. We start off at this point here. I have two actions, which is move to the left or right, I guess, or not move, stop, right, or a null action. And in this maze on the right, I can get this coin. Sorry, I gave this in Japan, so it was a 100 yen coin. But maybe I'll put a penny, which I guess doesn't exist, or they're not making them anymore. So maybe eventually it'll be worth more than a penny. But imagine a penny over here, and I have my pot of gold over there, 100 points. Right. And I have 2 oracles. K is equal to 1, K is equal to 2. And so what I have policy 1 says I'm going to go. This is my oracle. Oracle 1 says I go to the right, and it has a value function of 1, so you can get a point, right? So if I was doing, I might just choose to follow this. Well, I should say, let me let this build first, and then it'll be clear. Other policy 2 says no, go to the left and then stop, but its value function is 0, right? So in this state, if I were to say just pick the best oracle, I'm going to pick oracle 1, and I'm going to get this point, right? I'm going to get a point. Okay, maybe that's useful, because it looks better, at least in terms of value functions, than oracle 2. But what if I followed oracle 2 and went to the left? Yeah, so that's what that's what we would get. But if I were to go to the left and follow oracle 2, if I were in that state, oracle 2 might say stop, and that's why its value function is 0. But in that state, now oracle 1, which previously it said, from over here it said go to the right, now oracle 1 is going to say go to the left, and it's going to get 100 points. So in this example, I'm better off in the beginning following what I believe at this point to be the worst policy, which is a value function of 0 and going left, because that brings me to another state where oracle 1 is better. Right? So this is clearly, obviously better, right? Because we're getting 100 points, not 1 point. And so the way that we're going to do this is we're going to look at, again, this is similar to what's used for policy improvement, this advantage function. I think I'll go quickly through the sake of time. Huh?
10 minutes.
Oh, jeez. Too many questions. Okay. So again, we have this advantage. So basically, okay. So we look at the advantage function. The details are this is a paper at ICML 2023, and then there's another one at iClear last year. The problem with this is I don't know the V's. I don't know the value function. I don't know how good each policy is. The only way I can figure it out is through basically trial and error. I have to try different states, ask what the oracles would do, mimic them, and see how much return I get, how much reward I get, and estimate their value function. And so this becomes an online learning problem. And so the way that we're going to optimize this, and again, this is basically, we have this objective, it comes from this Mamba paper, this 2020 NeurIPS paper. They have this objective, and I can go through the details later, but it combines this imitation learning loss. So if you set lambda equal to 0, this becomes, you can show, this is a standard behavioral cloning imitation learning loss. Right? This is just mimic the oracles. When lambda is equal to 1, this becomes a standard RL. So you just maximize return. So by choosing lambda not 0 or 1, we can get this combination of imitation learning, but also using reward feedback. And so that's what we do. Again, I'll skip through the algorithm. But basically, the way that we do this, we have what's known as a roll-in period, where we follow the learner's policy first. So the learner's policy, which is initially random, we do what it tells us, up to some point in time that might be stochastic. At that point in time, we say, okay, from now on, or from the rest of the episode, I'm going to follow an oracle. The question is, okay, which oracle do I mimic? So we have some estimate of their value function with some, uncertainty, discrete or depending on its discrete or continuous. Basically, all this is just a count, state visitation count. That's all this is. So the more times we've seen the oracle in this state, this goes down, so less uncertainty. And then what we're going to do is we're going to use that to pick which oracle we're going to, what's called roll out. So that means from the rest of this episode, I'm going to roll out that policy, and roll out, do what the oracle tells us, and we can use that to estimate the value function. Okay, so I think for time, so we evaluate this in a number of sparse and dense reward domains, all in simulation, again, using standard benchmarks that are used for learning from suboptimal oracles. What we're showing in green is our method. So MAPS is our method that has, so it does quite well in these sparse reward settings, even in some dense reward settings. Other dense reward tasks. So with the purple here, or blue, is PPO. So it's a standard RL method. Sparse reward again doesn't do very well, but dense reward it does reasonable, and in this case it actually beats us. So I'll maybe I may or may not have time to talk about our next step is how we deal with that. But another interesting thing to look at is, okay, how does our model behave in terms of querying these oracles? Because it's trying to mimic it, trying to figure out which oracle is better in which state, and then try to mimic it. And so we compare ours. So we'll start on the right. This is Mamba, and what I'm showing here is over time, we have 3 oracles. This blue one, I should have changed the color, but blue one is a good oracle, so it's generally a good policy. Red is a really bad oracle, just everywhere uniformly bad. And then green is a mediocre, green here, blue is mediocre. Poor color choices. Very poor color choices. And so we see what Mamba does, is Mamba basically is flipping a 3-sided die every time, but equal likelihood querying the different oracles. So this is the previous state-of-the-art baseline. This is our method. So early on in training, not surprisingly, it doesn't know anything about the oracles. It's flipping a coin, rolling this 3-sided die and picking equally between them. But what we learned over time is that, well, look, this oracle 0 is really good. And so we start querying it more often. And it might be that actually these other oracles are good in some states. They are better in some states. But generally, oracle 0 is much better. And so our method is learning that it should pay more attention to oracle 0 and less to the others. Okay. But again, we have this issue where we are still, as I show, PPO-GAE is beating us in some sense when there's dense reward. So just very quickly, what I'll show is we have this pretty simple framework. This was at iClear, where really essentially what we do is we have our oracle set. These are our 3 drivers here. And basically what we do is we add the learner as an oracle. So basically what that means is the learner can, after they're in the roll out period, can choose not to imitate one of the other, or not to imitate another oracle, but it can sort of imitate itself. It can sort of ask itself in some sense, what should I do now? And again, I'll go through this for the sake of time, just show since this is RPI. And this now does what the show. Now this is that same environment where our method was beat by the standard RL algorithm because it was using reward feedback. Now we're able to beat it because really what this is allowing us to do is it's allowing us to blend imitation learning and RL. So effectively by adding our policy to our oracle set, lets us just to essentially evolve to pure RL. And so again, if we look at this querying the learner, so now we have 4 oracles. I'm adding the learner there too, right? Because the learner is now an oracle. Again, I don't remember which oracle is which in terms of how good they are. And initially, again, early on, we're probably querying them equally as likely. But over time, we end up querying the learner more because now the learner can actually outperform any combination of the oracles. So, how much time? 5 minutes? We started late. Okay. So, what is another way we can do? Maybe we can actually imagine, and again, there's a lot of follow-on work that Hung has done on this by now extending this to offline RL, where the oracles now, you could think of these as data sets that we have access to. But I don't have time for that. What I will talk about is, well, what is another way we can learn from suboptimal demonstrations and maybe use these as a form of reward demonstration. So, one way we can get them, again, even, like I said, as the bullet says, even non-expert robot demonstrations are hard to collect, right? It takes, you need a robot, you need people who are sufficiently proficient, it takes time. So there are, I should say relatively scarce, they are scarce. Robot data is scarce. Teleoperated robot data is scarce. But we have a lot of video of human data. So this is a project with Teddy and Kevin, who was at UChicago, now is at NYU, and Michael, on now learning from human videos, right? And the idea is that this is Ego 4D. Again, it is very small by many standards, but you can imagine a robot going, scraping YouTube. And so we have this method called Progressor. And what Progressor does is it tries to, again, you can formulate it in various different ways, but one way of thinking about this is to learn a dense reward from human videos. And the idea is fairly simple. What we do is what we'd like to be able to do is we like to have a model. This is our model Progressor that can watch a video of a robot performing a task, and it has access to the initial image. I can't see what's going on in this. Like, I don't know, doing something in a kitchen. There's an initial image. We assume we have access to the goal image, and we're given an intermediate image somewhere along the way of the robot or an agent doing something. And all we want to do is we want to predict how much progress is being made from 0 to 100%. And you can imagine using progress as a reward signal. So as a dense reward signal. So as progress is going up, we're going to provide more points to the RL agent. So now it doesn't get only 10 points when it loads the dishwasher. Now it's getting points when this model says, hey, you're making progress towards the dishwasher being loaded. So now we can get dense reward. So how do we learn this? Well, we can learn this from human videos. So we can scrape human videos. We take a subset of a video, fairly arbitrary length. We take the first frame, the last frame, and some intermediate frame. We have the timestamp, so that gives us a supervision in terms of progress. Is it 5 seconds in or 30 seconds in? So that gives us that gives us a measure of progress, and so we can train a model just from human videos to predict how much progress is being made. And now, surprisingly, yeah.
Have you considered doing data augmentation where you reverse the arrow of time and consider the fact that you could have unprogress if you're going the other way?
We did talk about this at some point. We never actually did it. But you could do that, yeah. There's a lot. I think there's a lot that we can do. This is arguably very simple. What we're doing here. Now, using this for RL is challenging for a few reasons. Not when the robot is doing things correctly. Surprising, this maybe it may or may not be surprising. This model trained only on human data actually does a good job predicting the robot's progress. Now the challenge is when so what we're going to do is we're going to use this as a dense reward to train a robot. So what is that? What's going to happen? Early on, the robot's in the kitchen. It's going to be flailing its arms randomly. That's going to be out of distribution, right? Because most videos of humans, they're not flailing their arms randomly. They're actually doing the task. So the model doesn't know what to predict. So we have some ways we call pushback of dealing with this early behavior that is out. Oh, here, next there we go. Early behavior being out of distribution. I think for the sake of time, I'll skip through this. But basically, we recognize or we tell the model that behavior is suboptimal, that it should downweight its progress, push it back, and that's all this is saying. So this is a distribution over progress, and then over time we have it. We push back less because the policy is becoming more proficient, and we can use this as a reward for training a policy using standard RL. Okay, yep. So we do this on a number of domains, again, a lot in simulation mostly. Training only from this no task reward. We don't know anything about the task. And I should say, importantly, our reward model is universal. We have one reward. Other previous work had one reward model for reach, one for pick and place, one for door open. We have one model that we're using for all these tasks. So we had no task feedback. The only reward we get is from our self-provided, our progressor model. And again, for the sake of time, I'll skip through this. It works well. It doesn't always outperform baselines, but in many settings, in most settings, it does. So just to show, this is, again, pretty simple, picking up a cup and putting it in a bin. We trained our reward model only on human videos this was Epic Kitchens, right? Epic Kitchens. This is a prediction of the progress that's being made. So we never saw a robot do this task. I'm sure somewhere in there was a cup put in a dishwasher, a cup put in a cabinet or something. But it's recognizing that the robot is making progress. And I'll just say one thing that we can do with this, again, is we can take this and we can assume, what we did is we took 20 demonstrations of the robot performing a task, 10 of them bad, so they pick up the cup and then they drop it, and then 10 of them good. Imagine we wanted to train an imitation learning policy. Now going back to what I was talking about before, these are oracles, right? These 10 demonstrations are bad, that's one oracle, and then these 10 demonstrations are good, that's a good oracle. What we could do is maybe just standard behavioral cloning is try to fit both of these demonstrations, assume they're both optimal, and train a policy to fit both of them. That's not going to work well. If we knew that the 10 were bad, we can just throw them out and only train on the 10 good ones, and that might work reasonably well. But the 10 that are bad are not entirely bad. They went and they picked up the cup. So that part of the trajectory is good. It's just the dropping that's bad. So maybe I just want to mimic the part of them that's the good part, and don't worry as much about mimicking the bad part. And so we can do this with our model because our model tells us for these bad demonstrations when progress is being made and when progress is not being made. So we can look at the state action pairs when progress is being made and say, try to imitate those and ignore the ones where it's not. And so that's basically what we did. So I'll just let this play. Okay, the time. But this is a standard one of the state-of-the-art methods at the time. So this is just at ICCV a couple weeks ago. This is VIP, and this is our model progress. Again, it's not loading a dishwasher. It's doing something very, very simple. Another task is opening a drawer. Is another baseline we compared against R3M. This is actually a pretty challenging task, especially with this pretty clunky manipulator. So you can see R3M does something reasonable. It reaches towards the drawer, but it misses it. This is pretty consistent that we saw this behavior, whereas our method, you can probably guess, it's going to open the drawer.
What are the chances?
What are the chances? But again, doing this, and just an interesting thing to look at, just very quickly, and then we'll cut it, is that this is showing, again, we have two sets of demonstrations. There are good ones and bad ones, and we're predicting the progress. So this is the one of reaching towards the drawer. So our bad demonstrations in orange reach towards the drawer, but they just missed it. So our model predicts that as you reach towards the drawer, that's good, but then progress drops off. Whereas the ones that are good keep going up. So our model takes this into account automatically when weighting this behavioral cloning loss. So it tries to mimic both trajectories here, and then only the good trajectories here. If we look at VIP and R3M, they are mixing up, they can't tell the good demonstrations from the bad demonstrations. That's part of the reason why they don't. And so that's it. These are the papers, and they're all on on GitHub all on the website with code. Okay.
Maybe a quick question? Yeah, quick. Oh, sorry, who's it?
Yeah.
That's a question.
Shoot.
So this model, the visual model, is basically just some vision classifier that you're training to, given some state in this trajectory, tell me how far am I?
Yeah, it's regressing to the value between 0 and 1.
But is this just a vision?
Yes. Yep.
I'm wondering, in the learn representation there, because you're kind of validating that, can you get basically a reachability graph from some embedding space there?
Okay,
that
yeah.
you can actually then
Yeah, I assume we've not really looked at
similarities
yeah,
within
yep.
this, right?
Yeah.
That would be really
And that's how some of the baseline methods do it. They approach it the other way. They learn a representation and then they measure distance in that representation
But you
as a
might
measure
get
progress.
that for
We would
free.
flip it.
You
Yeah.
flip it, right?
Yep.
But you might get that for free.
Yeah. Yeah, we've
That's
not.
like training. That would be cool.
We talked a little bit about looking at the representations, but I don't think we have, right, Judy? Yeah.
Yeah, we didn't see that part yet.
You showed some two examples, but will they work in adversary environment, they believe almost living in wartime, they in war, so will it work in the adversary environment and something like challenging something?
I mean, none of the settings that we looked at were adversarial. There was no agent trying to make the task harder. You can imagine you could some of these methods train it, and if it had training data that was adversarial, then you could deal with this. But we haven't looked at that.
Okay, let's thank Matt again. And